The main task of infrastructure managers is to ensure that infrastructure works, meet the needs of society. This involves determining when and where to execute interventions, including those to reduce the potential impacts of natural hazard events. Part of this process requires assessing the risk. Since infrastructure managers face unique situations, for example, with respect to what infrastructure they have, the hazards of main concern, and their available expertise and time, risk assessments for all infrastructure managers can only be done in the same way at a very high level. The high-level process constructed in this research, which can be seen in this figure, can be used in a wide range of situations. It consists of simulating system behavior in specific situations, as well as estimating and evaluating the risk, that is, conducting a stress test. The process encourages an iterative approach, where risks are to be first evaluated in a general way, and then increasingly in more levels of detail in future steps, until it is decided that the level of risk is either acceptable or not. Therefore, it encourages only obtaining as much information as required at each iteration. If the system passes or fails the risk assessment, which means passing or failing the stress test, interventions are planned if required. The setup risk assessment task is to determine what needs to be checked to be able to say that there are acceptable levels of risk. That is, which stress test should be conducted. This task includes the generation of preliminary thoughts on the area to investigate and the time period to be considered, as well as the definition of what the acceptable levels of risk are. The thoughts in this task affect the definition of the system representation, the requirements to conduct the risk assessment, as well as the scope and the level of detail of the assessment. It is a difficult task in that it requires multiple persons bringing together their opinions and feelings into multiple coherent questions to be answered or stress tests to be conducted. In this task, it is often realized that although there is a general agreement to what the problem is, there are many differences as to why there may be an acceptable level of risk. Structured brainstorming, such as general morphological analysis conducted by Ritchie Consulting in this project, is often helpful, especially when groups of people with substantially different opinions and backgrounds are involved. Scanning large databases is also helpful, such as that developed by Gavin and Doherty GeoSolutions in this project, to have an idea as to what scenarios and events could be of particular interest. This task ends with clear questions to be answered to be able to say that there are acceptable levels of risk, that is, a clear definition of the stress test. The determining approach task involves making numerous decisions about how the stress test will be conducted. These decisions include which type of approach will be used, for example, qualitative, semi-quantitative, or quantitative, whether or not computer support is needed, what level of involvement of representatives from different stakeholder groups will be required, and how multiple risks are to be aggregated. The defined system representation task involves determining how the system will be modeled. The system definition consists of all things required to determine if there are acceptable levels of risk, including the natural environment, for example, the amount of rain, the amount of water in the rivers, the physical infrastructure, for example, the behavior of a bridge when subjected to high water levels, and human behavior, for example, traffic patterns when a road bridge is no longer functioning. It also includes the spatial and temporal correlation between events and activities within the investigated time period, the consideration of assumptions, agreements as to how the system will react in specific situations, and the consideration of cascading events. The defined system representation task involves 5 sub-steps. The defined boundaries task includes the definition of spatial and temporal boundaries. The definition of spatial boundaries defines the part of the natural and man-made environment to be specifically analyzed and modeled, as well as how it is to be subdivided. This includes the definition of where the objects are located, where the source and hazard events can occur, and where the consequences could take place. The spatial boundaries are different and depend on the part of the system being analyzed. For example, the infrastructure to be considered might be that inside the physical boundaries of a city, but the rainfall that might lead to flooding might be that of a catchment area, which is much larger than the physical boundaries of the city. The definition of the temporal boundaries defines the time period over which the natural man-made environment is specifically analyzed and modeled, as well as how this time period is to be subdivided. The defined events task involves identifying all events, cascading and non-cascading, that are to be analyzed and modeled. In general, these events are grouped from source events, for example, the events considered to simply happen, at least from a modeling perspective, to societal events, for example, the events to which human activity can be associated, and therefore a value can be placed. The 5 basic types consider source events, hazard events, infrastructure events, network use events, and societal events. Examples are given in the table. All events are described in space and time. Measures of the intensities of interest should also be given. The Define Scenarios task involves linking the events together from the source events to the societal events in the form of an event tree. A very simple example is given in this figure. To build a tree, it is necessary to determine the value of the intensity measures defined in the Define Events task that will provide clarity on how events are considered to be related. Particular care needs to be used in the selection of the appropriate scenarios to analyze. It is also important to define the relationships between the events. The relationships between the events is required to estimate the likelihood of each subsequent event in the scenarios. For example, in order to determine the amount of water coming in contact with a bridge during a flood, it is necessary to know that a certain amount of water that falls as rain reaches the river seeps into the ground. Another certain amount evaporates, and another certain amount is temporarily held in retention ponds. Once the relationships are defined, the models of these relationships need to be determined. The levels of detail of the models depend on the problem. For example, in some cases, it may be sufficient to use one-dimensional fragility functions, based on expert opinion, to estimate the amount of damage that a single building might incur during an earthquake. In other cases, it may be desirable to use multidimensional fragility functions, such as those proposed by the University College London in this project, to estimate the amount of damage a large dam might incur during an earthquake. Additionally, the choice of model depends on the availability of data. One should not lose sight that the models may incorporate changes over time if it is desired. In a case where flooding is of interest, precipitation, runoff, the levels of water depth, contact of water with road sections, effect on road capacity, and impact on travel time are all not constant. In the Estimate Risk task, the probability of occurrence of each of these scenarios and the values to be attributed to the societal events associated with each of these scenarios are to be estimated and, when desired, aggregated. It includes estimate of all values specified in the Setup Risk Assessment task, that is, values defined in the stress test to be performed. In addition to risk estimates, the uncertainty related to parts of these estimates may be assessed, for example, the likely restoration times for hazard events of different intensities. Special attention is required to the certainty with which both the probability of occurrence and the consequences of each of the scenarios can be estimated. The sensitivity of these values should be investigated. The indicators of the sensitivity of these values are the divergence of opinion among experts, the availability of information, the quality of information, the level of knowledge of the persons conducting the risk assessment, and the limitation of the models used. The parameters bearing the sensitivity analysis should be the ones thought to have the most dramatic effect on the risk assessment values. If desired, one can also have interesting visuals to best understand where things are likely to happen for specific scenarios. For example, where flood water will extend, seen here in blue. Where traffic will be impaired, seen here in red. Where the damage on infrastructure is likely to happen, grouped here in clusters. As well as the extent of cost of specific types and how they are related to specific scenarios. For example, reconstruction costs of each of the areas in the previous graph. In the Evaluate Risk task, you verify the meaning of the estimated risk to persons that may be affected, also known as stakeholders. This is true regardless if a qualitative or quantitative approach is used. A large part of this evaluation is the consideration of how people perceive risk and the consideration of this over- or undervaluation with respect to the analyst's point of view, used in the estimation of risk. Another part, however, is stepping back from the analysis and reconsidering if everything important was modeled in a sufficient way. As systems are never modeled perfectly, it is reasonable that this task may lead to a decision maker deciding something different than the risk estimation alone would say. Such deviation should be explained. This task ends with one of the following decisions being made. The risk assessment has been performed satisfactorily and the risk levels are acceptable. The risk assessment has been performed satisfactorily and the risk levels are not acceptable. Or the risk assessment has not been conducted satisfactorily and more analysis is required. When the risk assessment is judged not to have been done satisfactorily, it means that it has not been done to a level of detail or in a way where you can say whether or not the risk levels are acceptable. This may happen because the system or parts of the system were not modeled in sufficient detail, or because there is too much uncertainty associated with the models used. If the risk assessment has not been done satisfactorily, you proceed to determine the parts of the system to be analyzed in more detail. If the risk assessment is either passed or failed, then you proceed to develop the intervention program, that is, determining the risk-reducing interventions to be executed in the near future. If the risk assessment is passed, then there will be no interventions included in the intervention program, and you're finished. In this task, the parts of the system that must be analyzed in more detail in the next iteration, if any, are determined. The parts that are likely to generate the most reduction in uncertainty in the risk estimation are selected. Care must be given to not only select parts of the system where risk is likely to be reduced in a way that will result in a passing of the stress test. To avoid preferential selection of system parts, the uncertainty related to each part of the system needs to be determined. In many cases, this will be done using expert opinion. This list of possibilities should include conducting tests on parts of the system, for example, load testing bridges and running more detailed flat simulation models. The parts of the system to be analyzed in more detail can be determined taking into consideration the available resources, including both effort and time frame. If there are resource constraints, the parts of the system to be analyzed in more detail should be the ones that will yield the largest reduction of uncertainty for the available resources. A process to assess infrastructure-related risk due to natural hazards with stress tests has been presented. It can be used by all infrastructure managers in a wide range of situations in which they may be, including variations of the types of infrastructure to be included in the assessment, the types of hazards to be included in the assessment, the expertise available, the time available, the need for detailed information, and the computer support available. More information on the process and an example using a road network and flat and last-link hazards can be found in the Libro 4.2. Probabilistic Solutions Consultant Training will now deliver part 2 of the presentation.
Process as presented in Part 1 to assess infrastructure-related risks due to natural hazards with stress tests will now be further elaborated on a conceptual level as well as an operational level. Let us first discuss the conceptual level, which follows the analogy with the actuarial stress test definition in the financial industry. An infrastructure stress test is defined as an analysis to determine whether there are unacceptable infrastructure-related risks for a given unfavorable scenario. Stress tests may help detect objects that, if strengthened through the execution of preventive interventions, will greatly decrease the infrastructure-related risk, i.e. hard engineering measures, and/or determine those non-engineering mitigation actions that will minimize the detrimental effects of a loss of functionality of the infrastructure, i.e. soft policy measures. A stress test analysis can conveniently be described mathematically as the construction of a conditional outcome probability distribution P of S I of S given S, A0, conditional on an adverse stress scenario S and a given status quo A0. The subscript I for the outcome O stands for the different types of outcome metrics. Typical stress outcome metrics for infrastructure systems are the costs of physical repairs to the network, delay times for network users, restoration durations for the network, and the loss of functionality of the network, all given for the specified stress scenario. An example of a missed stress test opportunity is the analysis of the risks of the nuclear power plant at Fukushima, Japan. The Fukushima Daiichi plant levees were built to withstand 5.7 meters wave heights, while the exceedance return period of 10-meter tsunamis was only a mere 36 years, as 14 tsunamis of at least 10 meters have been observed in the last 500 years on the Japanese west coast. Had the Fukushima Daiichi event been studied by way of a stress testing exercise prior to it happening, then one of the possible outcomes with probability greater than 0 would have been the outcome that we are currently witnessing, the outcome where a large part of northern Japan has been radioactively contaminated. In light of the fact that Fukushima Daiichi levees were only designed for typhoons, we find it plausible that the Fukushima Daiichi stress test would have compelled the relevant stakeholders to install also tsunami protection, or at the very least, move the power back up from the cellar to the roof. In InfraRisk, stress tests are being applied to infrastructural systems, such as road and rail networks. Infrastructural systems can be modeled as fault-free systems with a large number of dependent components. For instance, the bridge network on this slide may be modeled by a fault tree of 3 minimal cut sets component 1 and component 2, or component 3 and component 4, or component 3 and component 5. If one of these cut sets would occur, the connectivity of the system from H, home, to W, work, would be lost. There are two complications in this analysis. 1. If the number of components in the system becomes large, the size of the fault tree grows exponentially. And 2. The components in the system might have some dependency or show cascading effects. If component C1 fails, it may be likely that component C2 will also fail, if the cause of failure is scour due to high river discharges, for instance. Our stress test analysis should deal with these complications, for which some novel algorithms have been developed within the InfraRisk project. Let us now look at an operational level to a stress test analysis. The stress test framework basically follows the following 6 steps. 1. Generate a stress scenario, for instance a 1 in T years earthquake, which involves expert judgment to decide about the return period T, as well as statistical extrapolation of the historical earthquake datasets. 2. Generate a spatial hazard map, for instance a spatial PGA map. For this, physical models are needed. 3. Generate a probability map via conditional fragility curves, which describe the failure probability of a component within the system, given the intensity measure to which the component is exposed. 4. Select the damage state scenarios from the resulting probability map. Because of the huge number of possible scenarios, clever algorithms have to be applied. 5. Given the selected damage state scenarios of the system, consequences can be estimated by using, for instance, a Nexta estimation of travel time delay model. Finally, in 6, the outcome metric should be evaluated. For this, a novel criterion has been developed. These 6 steps will now be further discussed. Step 1. Stress scenarios can be based on historical scenarios, employing shocks that occurred in the past. Or they can be based on hypothetical synthetic scenarios, constructed to take account of plausible changes in circumstances that have no historical precedent. 2 other techniques that are often included under the rubric of stress testing are extreme value theory, which applies statistical analysis to the tails of return distributions, and the maximum loss approach, which estimates the combination of factors that would cause the largest loss to the system under consideration. Structured brainstorm sessions, such as conducted in General Morphological Analysis, Ritchie 1998, may be used to elicit this expert knowledge-based narrative from the relevant experts and stakeholders. One possible instrument by which to structure a brainstorm session is the use of Delphi panels and similarity judgment. Such a combined approach has been used, for example, to prioritize objects within the National Alert System in the Netherlands, prioritize the most vulnerable locations related to terrorism, Prague 2009. It is also often useful to scan large databases, such as the one proposed in Gavin and Martinovic 2014, to have an idea as to what scenarios could be of particular interest. Descriptions of what can be found in such databases in the case of infrastructure-related risks due to natural hazards can be found in Cheng and Talab 2014. Also, when using the extreme value theory approach, particular thought needs to be given here to the return periods at which the stress tests need to be conducted. For instance, the selection of a stress scenario for flooding involves the modeling of the annual maximum discharge levels at a certain location along the river. Expert judgment sessions have recommended for a particular case study to consider return periods of events with T is 200, T is 500 and T is 1000 years. In this slide we see the fit by a generalized extreme value distribution, including the worst case and best case fits according to a 2.5% and 97.5% confidence level. It is not only the intensity but also the duration of the flood wave which is of importance. Both intensity and duration allow us to construct hydrographs. Step 2 involved the mapping of the stress scenario on a spatial hazard map. For flooding, a linear hydrodynamic modeling approach can be adopted for this purpose, in which the river cross-section is simplified to a prismatic box with a certain flow carrying width and a certain storage width, a given constant slope and a given roughness coefficient. This slide shows how the flood propagates in time and space in downstream direction. In step 3, the spatial hazard map is converted to a probability map, which shows the probabilities of being in a certain damage state of all the components in the system. These component probabilities are determined by fragility curves in combination with the occurring intensity at the geographical location of the component. Challenges occur while trying to implement a stress scenario regarding the computational complexity. Deliverable D6.2 has developed clever sampling methods based on a nested sampling NS and probabilistic sorting algorithm PSA to reduce the computational efforts. By projecting and sorting probability columns to the vertical axis, multivariate systems can be represented by univariate systems. By cutting off the tails, a considerable reduction of computation time can be achieved while maintaining acceptable accuracies. In step 5, the selected set of damage state scenarios should be propagated through the outcome metric model. Basically, this involves substitution of each individual damage state scenario into the outcome metric model and presenting the outcome probability distribution as shown in this slide. In the last step, an evaluation of the stress test outcome probability distribution should be made. The level of risk that is considered acceptable will typically vary from situation to situation, as risk acceptability is inversely related to both the number of cost-efficient alternative courses of action that may reduce the risk and the extent of that cost efficiency. That is, the unacceptability or acceptability of some current risk is something that has to be demonstrated by all parties involved. In part 1, it was shown that stress tests are meant to detect objects that, if strengthened through the execution of preventive interventions, they will greatly decrease the infrastructure-related risk. So the strengthening of one or more infrastructural objects are the alternative actions which are open to the infrastructure manager, relative to a status quo where he or she only performs regular maintenance. Moreover, the infra manager will have some budget constraints under which he has to decide whether or not to strengthen additional infrastructural objects or not. The evaluation of a stress test outcome distribution can therefore be based on a comparison with another outcome distribution. For the comparison of outcome probability distributions, a Bayesian decision theoretical framework has been proposed. In deliverable D6.3, it is derived that the comparison should be based on the worst, average and best case scenarios. Let us assume that we want to evaluate the outcome distribution given a decision D1 in a network versus the outcome distribution given decision D2. Let us look at the lower bounds and upper bounds of these distributions. We notice the difference between the lower bounds is larger than the difference between the upper bounds. This results in a preference for decision D2. Or equivalently, we choose D2 because the sum of the lower bound and the upper bound of D2 is larger than the sum of D1. Finally, it is derived that the decision-making or the evaluation of a stress test outcome can be based on one single measure, which is the summation of the lower bound, expected value, and the upper bound of the outcome distribution. This is in contrast to the traditional evaluation, which is usually based on expected values only. Part 2 has shown how the stress test fits within the overarching risk assessment process as presented in Part 1. Stress tests are basically a special instance of a risk assessment, where instead of marginalizing over all the possible stress scenarios, one specific stress scenario is chosen instead for which to gauge its potential effects. The stress test framework is simple enough on the conceptual side. On the practical side, however, when one wishes to implement this framework, things can quickly become non-trivial, for which novel sampling algorithms and a novel evaluation protocol have been proposed.